We're going to continue looking at ecosystems now, specifically starting with the idea of the carbon cycle. Now, we talked a little bit about this before, where the carbon cycle we know moves from the atmosphere into the organisms through photosynthesis. From photosynthesis of plants, consumers eat those producers that did photosynthesis, and then it moves through the food webs, food chains, and eventually the death of the organism will put some of that carbon back into the atmosphere, and other nutrients will go into the soil. And of course, along the way, every time an organism respires, it also puts carbon back into the atmosphere. But we get this cycle. And so carbon moves through all food webs, and it's in certain reservoirs. The Earth's crust is one place with a large amount of carbon. Again, that's really not one that's extremely accessible to us. The ocean is also a place where carbon is a place that can be absorbed. Fossil fuel reserves are another place where carbon can be absorbed. Detritus in soil is going to be living, or should say non-living at this point, dead matter in the soil that contains carbon as part of being carbon-based organisms. And then there's the air, and then there's just biomass. So as you can see, the actual biomass of the planet has the least amount of place where carbon can go, but for us it's the most accessible in terms of a place to put carbon. We really don't want to put it in the air, as we're going to see, and we really can't put it into the others so easily. So remember that the carbon cycle goes from atmosphere into the biosphere, those living organisms that are in the food chains and food webs. And then of course there's the dead portions where things decompose, and then it goes back into the reservoirs like the atmosphere and the ocean and so on. And of course burning fossil fuels can put that back into the atmosphere, where otherwise it had been in the fossil fuel for a very long time, stored away as a reserve underground. And so each year we withdraw 4 to 5 gigatons of fossil fuels from our environmental reservoirs. And then we put about 6 gigatons more carbon into the air than actually that the oceans can handle. And if you remember, the oceans actually hold a whole lot more than the air does, but there is a limit to what the oceans can absorb. And at some point, having too much carbon dioxide in the atmosphere will make it too acidic for living things to live there in the way that they currently are. And so again, what happens is that the excess carbon ends up in the atmosphere, and if, of course, as we're seeing, global climate change can be affected by excess carbon dioxide. Now, an important question I want you to think about, and if you will, take a moment and pause after I ask this question. Literally pause the video and ask yourself, where is carbon in an ecosystem? So go ahead and take a moment. Okay, so hopefully you've asked yourself that question, and I want you to think about some of the places that you might find carbon, and then why would knowing where the carbon being stored be so important? Okay, and where it's normally used. Why is it so important that we know where these things take place and are stored in the ecosystem? Go ahead and stop again, pause the video, and think about that. Okay, so hopefully you actually paused the video. Most of you probably didn't, but I understand and I know how this works. So where is carbon? Well, carbon is where anything that is organic will have carbon. So that's one place. So a living organism, dead organisms, where dead things have decomposed, those things will have carbon, as well as carbon dioxide in the atmosphere. And understanding where carbon can be is really important, because if you put more carbon than is normal in a location, can that affect various things? Like put too much in the atmosphere and it creates more of a global warming effect because of the greenhouse effect, or put more into the ecosystem, except the ecosystem has to have a way to absorb that carbon, and if you don't, then it doesn't go into the ecosystem, so it has to go somewhere, back into the atmosphere or into the ocean. Okay, so as we're going to see, understanding where carbon is makes a difference. Okay, because we can take carbon out of the atmosphere. One of those things we can do is to absorb carbon through planting trees and other plants, because they do photosynthesis and take it in. So this is just a carbon budget, looking where carbon is at in this whole system. It's a hardwood forest ecosystem. It's in the dead stuff, it's in the living stuff, it's in the atmosphere. Some of it is above ground, some of it is below ground. But just understanding where the carbon is at will help you to know how to remove it from that location and also to keep it from moving to places you don't want it to be, like in the atmosphere or in the ocean. We can measure where carbon is located and how much carbon is found. There's the FACE facilities, free air carbon enrichment facilities, where we can even test what a large amount of carbon does to an area. And so we have these different apparatuses set up so that we can actually test what's going on when we basically we'll pump in a bunch of carbon into these areas and then just see what happens to those locations. We measure the carbon around the world, and we try to get an idea of where and how that carbon is coming from, how does it get there, and what effects does it have. And so we don't measure just one area, we measure the entire planet with lots of carbon measurement sites, not just in North and South America, but as we've seen, Hawaii, as well as China, all the continents. So we can measure carbon and seeing how much it's increased. Now what we've noticed is that over time, just like the human population has increased, as we see with this red line and the little dip here, we talked about that last time, there are different points in time in our history where the population has gotten larger, but also there are events that have happened. As we started to work outside of just hunting and gathering food, we did agriculture and we started metalworking, irrigation, so we actually started to kind of change our agriculture, the industrial era. As we see the population getting larger and more things that we as humans can do, we start to see that fossil fuels get consumed more. How do you run a factory without electricity? Well, to make electricity, or in the previous times, we would run the factory off coal itself. You can make electricity from coal, which is a fossil fuel. Of course, we run cars off of gas, which is a fossil fuel. And so we see lots and lots and lots of fossil fuels being used more and more as we have gone from since the Industrial Revolution started. Now, there's a lot of carbon, as we can see here, increasing over time. And it matches up with our population. As the population gets bigger, we see more carbon use. We see it in petroleum, we see it with coal, we see it with natural gas. Even with cement production, there's an addition of carbon that's produced into our atmosphere. Have you ever looked out over a large city and seen smog? This is Mexico City, one of the largest cities in the world, and they have smog, and you can't see as far as you should be able to. Los Angeles has this problem. A friend of mine just posted a picture on Facebook that showed the smog over, I believe it was maybe Houston, that she could see from where she was at. And you just see in large areas that you can't see as far. Now, that's pollution. That's not smoke. It's a mixture of, the name smog even comes from smoke and fog, but it's a bunch of particulates that have made it into the atmosphere from burning things, some of it being smoke. Some of it is just from combustion of other things like fossil fuels, and these things end up in the atmosphere. And it doesn't just stop your sight from being able to see as far, but it actually is something that you can breathe in, and it damages your lungs. But it also can even trap heat into an area or reflect things away from the area in terms of light. So what we're seeing is as carbon dioxide goes up, we see temperature go up. We also see, not just with carbon dioxide, but there are other gases that fall into the greenhouse gas category, like methane. Okay, so it's not just carbon dioxide, but there are others. As we see carbon go up, we see temperature go up, even with a little bit of the up and down that you see every year with that yearly cycle with plants starting to grow and take in carbon dioxide during their growing season, and then of course as it they die off and maybe go dormant, we start to see them go up, the carbon go back up again just a little bit, and that's because they're not taking it in and doing as much photosynthesis. But even with that yearly cycle, we see a trend of the overall increasing carbon dioxide, and along with it, temperature. Now, how do we know that today's increased atmospheric CO2 is from fossil fuels? Well, people might say, oh, this is just a natural thing. It's not a natural thing, and the reason for this is that we can actually measure the carbon that's in the atmosphere, and there's different kinds of carbon. And you can measure the carbon C14, um, and we're finding that the concentration of C14 in the atmosphere has decreased with the burning of fossil fuels. Fossil fuels don't give off carbon-14, they give a different isotope of carbon. So we're seeing the natural carbon that's produced from breathing, from our normal uh, respiration, that carbon-14. And what we're seeing is that there's actually a difference in the kind of carbon that's in the atmosphere. The carbon that should be there from just breathing and doing respiration is going down. And that's what we see in this graph. But we know that carbon is going up. And so what carbon is going up? It's the carbon from burning of fossil fuels, the different isotope of carbon. And so overall, when we look at the Earth's global temperature, with carbon we see temperature going up. They're together. Carbon and other greenhouse gases are trapping heat into the atmosphere onto this planet, and it's not able to escape. And while that's a good thing, the greenhouse effect is not a bad thing. It's how we're able to stay warm enough so that we don't freeze. The problem is that we're allowing it to get worse in terms of holding too much heat, more heat than we really like. And the planet doesn't like this. The planet doesn't respond well to this, and it affects temperatures, it affects ecosystems, it affects weather. So as we see with the greenhouse effect, this is the radiant energy from the sun being absorbed by the Earth's surface, and it's radiated back as heat. The problem with the greenhouse effect is that the gases up there act like a blanket and trap some of that heat onto the planet. And so just like in a greenhouse, if you've been in the one here at the W, you can see that light comes in, but it stays warmer in there than it may be outside because the air is not able to move around. And instead of being radiated back out, it gets trapped. So carbon dioxide, water, nitrous oxide, methane, even chlorofluorocarbons, have you ever heard of CFCs? These are also used to trap in heat into our atmosphere. And the more we put up there, the more they can trap. And so global warming is just this idea that the sun hits the planet, a lot of it radiates out, but because we're increasing the CO2 in the atmosphere, less of it's able to escape, and parts of it will bounce right back. So it's not just methane, it's not just carbon dioxide, it can even be water vapor that traps in these gases. So what we see is that atmospheric carbon dioxide fluctuates annually with the patterns of photosynthesis. During the growing time, photosynthesis goes down a little bit. When plants stop growing or start to go dormant, they're not doing as much photosynthesis, and respiration is happening more. Then we start to see an increase again. And this happens on a yearly basis. But then when you look at the overall average of CO2, you start to see that they're increasing overall in the atmosphere, and that these increasing CO2 counts are coming mainly from human activities, from burning of fossil fuels, and this is increasing the greenhouse gases. Now look at this. In 2001-2002, this is deviations from the mean temperature. Some places are getting really hot, and there are even a few places that are really cold, colder than normal by almost a degree. Some places that are 2 to 4 degrees hotter. I don't know about you, it's a little scary. There's places that are hotter, like Siberia, Northern Europe, the Arctic. Those are places that usually have ice. This ice is melting, and you can see glaciers receding because it's so hot. So when I was growing up in the 1980s and 1990s, we heard a lot about the global warming, and that we should be really careful about global warming and don't use hairspray that has, CFCs in it. And so what happened is that we talked a lot about increasing the mean global temperature, due to increasing the greenhouse effect, of course, and this comes from having a lot of CO2. But as we've learned more, the idea of global climate change comes along. In the 1990s and early 2000s, we see it's not just a warming of the planet, but this affects the way weather works on our planet too. So we have an increased climatic variability, which is driven by regional changes in Earth's climate. Okay, so it's not just an increase of temperature, but this temperature increase is actually affecting how the weather works around the planet. And not just weather, but the climate of the planet. And those are not quite the same thing. Climate involves weather, but climate is more of a big picture, overarching idea, where weather may happen from day to day. Climate is pretty much a pretty stationary thing, except that we're able to change it some in this case. And let me explain. We live in a temperate climate that doesn't get really hot and it doesn't get really cold. But if you go to Central America, you're going to find some really hot climates. They're tropical climates. Okay, these are opposed to being weather, where one day you might have rain and another day it might be sunny. That's weather. Climate's going to be what you see on a broad basis. And so, of course, this kind of increase of temperature and then the climate change is going to affect these biomes that we see. Tropical areas, Arctic areas, they're going to be affected. Some of these places may flood eventually, and that's going to be a little scary. Some of these places might dry out. Some places may not have enough water, and some places may have too much. Now, what's really interesting is if you look at global primary productivity, this is NPP. Look, China, Southeast Asia, parts of India. We see a lot of South America, even sub-Saharan Africa. And then look, in the United States, there's the South is a very productive area. And this is a little bit scary because as we see these productive areas, these are the places that grow lots and lots of plants. And the plants, of course, absorb carbon. What happens if you cut down those trees in those areas? What happens if you build on that land and don't allow it to grow so much? That's what we're going to see, is that we have some of the most productive area in the country, and as we take away that land as a growing thing, as we take away forests, we're going to have less carbon dioxide taken in. And then here's where things get really scary. So this is a picture that shows the lighting up of the United States at night. And you can see there's lots and lots of cities, and that's where each light little represents. And look, it's a lot more in the east than in the west. So let's look at the south here for a second. Look at those spots. Okay, very interesting spots. Lots of little red spots, and those red spots are 16 to 128 or greater housing units per kilometer. That's a big jump from 8 to 16 to go 16 to 128. Now watch this. 1940, 1970, 2030 projection. That's a lot of red. That's a lot of people living. And that also means there's a lot of land that's now not under cultivation, now not under forested reasons. This is going to be a little bit scary because that land is now not going to be as productive. It's not going to be absorbing as much carbon, and it can affect things in terms of climate, not just here but around the world. And so we might have some global warming. We already are seeing global warming. A long-term increase in temperature near Earth's surface. So far we've seen about 1.8 degrees Celsius, about 3.2 degrees Fahrenheit. And this is projected to be how it's going to be from century to century. 3 degrees may not sound a lot, but imagine an average of 75 going to an average of 78. And so, you know, your extreme when your average is 75 might be 99 degrees. And then when you get an extreme of 3 degrees, you know, on top of that 78 degrees, this is normal, maybe it's 100 and something. And so it's just things are going to get hotter. So we expect to see things like melting glaciers, rising sea levels. I mean, there are people who live on islands that are already thinking about how they get off. And there are whole island nations that can go underwater once this happens. So it's going to alter where rain falls, the global precipitation patterns, where drought is at, where flooding is at. You're going to get more intense hurricanes. It's going to be kind of crazy.